All right, so here we are, section 9.2, atomic and ionic sizes. I probably could have taken that drink before I started filming this video, but I did not, and here we are. We move forward with our lives. Okay, so one of the things that we need to talk about with respect to atomic size is the relationship between the protons that are at the center of the nucleus and how much they pull all the electrons surrounding. Now, if you remember, we talked about electrons falling into two different categories. Those two different categories were they fell into the category of being valence electrons, or they fell into the category of being core electrons. Now, valence electrons, since they are the farthest out from the nucleus, they basically perceive less of the pull from the protons in the nucleus than your core electrons. And so what we have is this means of calculating basically the force that they're pulling, or the shielding that takes place because of those core electrons. And so what we do is we come up with this factor of S, which is equal to the number of valence electrons times, well, 0.35, and you add that to the number of core electrons times 0.85. So essentially what this means is if you have, let's say you have, well, here, we'll look at it here. If you think about a sodium or a magnesium atom, okay, at the center of a sodium atom, there are 11 protons, okay? That's 11 positive charges. Every single one of these electrons, for instance, this one, and this one, do not experience a pull of 11 protons. Instead, you have this shielding taking place. And so that's where we look at something like these 10 core electrons are going to be basically experience the most pull from those 11 protons. Same thing when it comes to magnesium. There are 10 core electrons, and these two electrons outside of that range are your valence electrons, and they're going to receive less of that pull than your core electrons. Now, this ZEFF is what's known as the effective nuclear charge, or so basically the pull from those protons. So it's just a nice way to kind of look at that number. So, or look at I guess, kind of the pull that each of these experiences. And so this isn't something that you're going to have to calculate. You might have a homework problem or two about this, but I really just want you to be familiar with the idea that those valence electrons do not experience the same pull as your core electrons. Atomic radius is the next thing that I wanted to talk about. Now, atomic radius generally decreases from left to right across a period. So across the periodic table, from left to right, this is going, the radius is going to decrease. Now, this trend is a little bit complicated whenever we're in this central block where our transition metals are, but when you are talking about your main groups here and here, that's a trend that you can respect. Atoms and ions get larger as you move down a group on the periodic table. So the atoms that are basically here, well, those are going to be the largest because they are going to be, well, yeah, so yeah, they're going to be the largest there. And we see that visualized here. Atomic radii of the main group elements. Rubidium, Rb, well, that has an atomic radius, which is measured in picometers, of 215. Helium, by contrast, the helium atom is 37 picometers. Now, that's the trend that you need to be familiar with respect to your main group atoms. Things are a little bit different, however, though, when you talk about cations and anions. Why is that? Well, with a cation, you have removed an electron, and therefore you have decreased the space in which that atom is going to cover. So all cations have smaller radii than their corresponding neutral atoms. Okay. Now let's think about the opposite of that, an anion. You're adding an electron, in which case anions have a larger radii than their corresponding neutral atoms. Okay, pretty straightforward. If you're adding an electron or if you're removing an electron, that's all you need to be that's all that you need to keep straight there. Here what we have is a representation of, let's just take this one right here, rubidium. Rubidium shows the size of the neutral element, Rb, is 215 picometers, whereas the rubidium cation has lost one electron, it's 152 picometers. So generally we like to compare a neutral atom to an anion or a cation and ask the question, well, has it changed in size? Yes or no? Has it gotten larger? Has it gotten smaller? Fluorine, whenever fluorine gains an electron, it goes from 72 picometers. That extra electron makes it 133 picometers. What has stayed constant when you're talking about this fluorine? Well, the number of protons have. The number of electrons has gone up. There are more electrons for those protons to basically keep within their grasp. And so that space of that ion is larger. Now, you have this sort of trend in ionic radii of the main group elements. And this trend is really fairly similar to the atomic radii. The only thing that's worth noting is the right-hand side of the periodic table is mostly your nonmetals, in which case those nonmetals, they like to form anions. So they're adding electrons, adding as many as 3 electrons, as is the case with astatine. And astatine, the ion that astatine forms, is larger than the ion that rubidium likes to form. Now, that really is just something that you need to appreciate as, is it forming an anion or a cation? All right, well, the takeaway from this is trends. Where are atoms larger? Where are ions larger? Where are ions smaller? That's about it. You got this, and let's keep going.